Imagine you're driving through a tunnel with an entire ocean above your head. Millions of tons of seawater pressed down, held back by nothing more than a seamless shell of concrete and steel. It sounds like science fiction, but it's real, and it's one of the most extraordinary engineering feats of the modern era. So how do engineers build a tunnel where the ocean itself is trying to force its way in? How do they deal with intense pressure, shifting ground, and complete separation from the surface to build a structure that will safely carry millions of people for generations? Well, that's exactly what we're going to find out. Undersea tunnels are not just engineering wonders. They change the geography of entire regions. Islands become suburbs. Port cities gain direct access to highways. Ferry crossings that once took hours disappear into a drive lasting only minutes. For countries built around coastlines, that transformation isn't just convenient. It reshapes trade, commuting, emergency services, and economic growth. But none of it begins with concrete. Long before construction starts, engineers must answer a question that no one can see simply by looking at the water. What's actually beneath the seabed? The answer determines whether the tunnel will last a century or never be completed at all. Before the first excavation begins, engineers become detectives. Survey vessels map the ocean floor in extraordinary detail, while drilling teams extract samples of the soil and rock hidden beneath it. Every layer is analyzed: soft sediment, fractured rock, hidden fault lines, underground water pockets. Each one could become a critical weakness if overlooked. The seabed isn't just a foundation. It's the biggest unknown in the entire project. At the same time, environmental specialists are asking a different question. What happens to everything already living here? Construction noise can disrupt marine mammals, sediment clouds can damage ecosystems, and entire habitats may need to be protected or relocated. Depending on the project, engineers reduce underwater noise, carefully monitor water quality, and sometimes even construct artificial reefs to replace disturbed habitat. Only after both the engineering challenges and environmental risks are understood does construction finally begin. The next question is how, and depending on the conditions below the water, the answer can be completely different. The first method sounds almost impossible. Instead of building underwater, engineers build the tunnel on land. It's called the immersed tube method. Massive reinforced concrete sections are cast in dry docks, each measuring roughly 712 feet long, longer than 2 football fields, and weighing more than 73,000 tons. Every segment is already complete, with separate chambers for highway traffic, rail lines, and maintenance corridors. When finished, each section is sealed, floated out to sea like an enormous ship, and carefully positioned above a trench that has already been dredged into the seabed. Then comes the moment everything depends on. The segment is slowly lowered into place until it connects with the previous one. Heavy-duty rubber gaskets are compressed between the two sections, creating a watertight seal strong enough to keep the ocean out. It's an elegant solution, but only where nature allows it. Strong currents, unstable seabeds, or rugged underwater terrain can make this method impractical. When that happens, engineers abandon floating altogether and choose something capable of carving its own path through the earth. Think of a machine the size of a small building, slowly eating solid rock and making the tunnel behind it as it goes forward. That's a TBM, a tunnel boring machine. At its front sits a cutter head nearly 39 feet across, fitted with 140 hardened steel cutting discs. It rotates slowly, less than 3 revolutions per minute, but pushes forward with roughly 5,800 pounds of force per square inch, enough to grind through solid rock. But cutting rock is only part of its job. As the machine advances, excavated material is carried away behind it, while enormous precast concrete rings are installed almost immediately, creating the finished tunnel wall only a short distance behind the cutter head. The machine excavates the tunnel and builds it at the same time. Every cycle takes about 90 minutes, advancing roughly 66 feet in a full day of operation. Yet even this engineering giant has limits. Some rock is simply too unpredictable. Some pressure conditions are too dangerous, and when that happens, engineers turn to a method that has existed for centuries. Sometimes brute force is still the best solution. Instead of grinding through the rock, engineers deliberately break it apart. The process is called drill and blast. Crews drill dozens of precisely positioned holes into the rock face before loading them with carefully measured explosive charges. The detonations are timed to the millisecond so the rock fractures exactly as intended, while minimizing unnecessary vibration. Within seconds, roughly 5 feet of solid rock can disappear. Despite its age, drill and blast remains one of the fastest and most cost-effective tunneling methods available. But there's one place where engineers avoid using it whenever possible. Shock waves that easily fracture rock can also disturb sensitive marine ecosystems. That's why underwater projects rely on other methods whenever conditions allow. But what happens when neither explosives nor a tunnel boring machine can safely get the job done? When engineers run out of modern solutions, they fall back on one that has existed for generations. They dig by hand. The process begins with a vertical shaft sunk from the surface to the planned tunnel depth. That shaft becomes the project's lifeline, carrying workers, equipment, fresh air, and excavated material between the underground site and the world above. Progress from there becomes painstakingly slow. Instead of blasting or grinding through the ground, crews carefully cut their way forward using hydraulic excavation equipment designed to disturb the surrounding earth as little as possible. Every newly exposed section is immediately stabilized. Shotcrete is sprayed onto the rock, steel arches are installed, and heavy rock bolts lock everything into place before excavation continues. There are no shortcuts here. Every foot has to be earned. When thousands of tons of seawater are pressing down overhead, patience isn't a weakness, it's a safety system. Finishing the tunnel doesn't mean the project is over. In many ways, it's only just beginning. Before the first driver is ever allowed inside, the entire structure has to prove it can survive exactly what it was built for. Many modern underwater tunnels are constructed with 2 traffic levels, allowing twice as many vehicles to pass through without increasing the tunnel's footprint beneath the seabed. Emergency exits are positioned roughly every 660 feet, while ventilation, lighting, drainage, communications, and fire suppression systems all undergo extensive testing. Engineers deliberately push the tunnel to its limits. They check for leaks, they test pressure resistance, they simulate fires. They verify that ventilation systems can remove smoke quickly enough for people to escape safely. Only after every system performs exactly as intended does the tunnel open to the public. But even then, the work is far from over. The day a tunnel opens is also the day its longest phase begins: maintenance. Hidden behind the concrete lining are hundreds of sensors quietly monitoring pressure, humidity, temperature, vibration, and structural movement every second of every day. Most drivers never notice any of it, and that's exactly the point. It's easy to admire the concrete, or the machines, or the engineering, but none of those things alone make an underwater tunnel possible. What really makes these projects extraordinary is the thousands of small decisions made over years of planning, construction, testing, and maintenance. Together, they create something remarkable, a structure capable of quietly holding back an entire ocean while millions of people travel through it without giving it a second thought. Would you feel comfortable driving through this tunnel? Knowing millions of tons of seawater are only meters above your head? Let me know in the comments. And if you enjoyed this video, don't forget to like and subscribe for more stories about engineering, mega projects, and the breakthrough technologies shaping our future. Thanks for watching, and I'll see you in the next one.